1, 2, 3, 1, 2, 3. Determinant of matrix inversion, line thickness 1. To facilitate the use of matrices, we need two additional mathematical objects that you could get from a square matrix, the determinant and the inverse matrix. Determinant of a small, why small? Surely not. Oh well, I should just keep reading. Small square matrices are well known. This and this. More generally, we define the determinant and iron matrix like this. Levicivita of order n indices. Yeah. N to the n permutation symbols if you rearrange them, but only n factorial of them survive because the rest of them are 0 because if any index repeated is 0. Okay. The order n of the matrix is called the order of the determinant. Okay. Just computing to show examples. The 6 terms correspond to the 6 permutations, 3 even, 3 odd of the indices 1 to 3. Properties of determinants that can be proved directly from these equations. We went through some, we were successful with some were a little... I don't think we got to the bottom of some, but we'll return to them at some point. The determinant of a transpose matrix is the same as the determinant of that matrix. Determinant of a matrix where one column is multiplied by a constant is the same as that constant multiplied by the determinant of the matrix. Okay. And the determinant of Ka, where each element is multiplied by K, is the same as K to the power n multiplied by the determinant. If A and B differ only in exchange of 2 rows of the columns, you add a negative sign. If A contains 2 identical rows or columns, the determinant is 0. Determinant of a product of 2 matrices is the same, like, commutative is the word. The determinant of AB is the same as the determinant of BA. And is also equal to the determinants of A and determinants of B separate multiplied. Hello, yeah. The expression of the determinant is a sum of determinants. The expression of a determinant as a sum of determinants of lower order is called a Laplace development. To obtain Laplace, we factor out one matrix element so that determinant of A is equal to the sum of the product of a matrix element times the cofactor, where the cofactor of the element AKQ does not contain AKQ. Where the cofactor CKQ equal this of the element AKQ does not contain AKQ, while the sum does not involve K. These restrictions are denoted by primes. Consider the reduced determinant of order n-1. Okay, M is obtained from the matrix in which the kth and qth column are removed, is identical to CKQ except the permutation symbol of n indices is replaced by n-1 indices instead, where you remove the k. By the reduced permutation symbol this n-1 indices obtained from dropping it from it by dropping Q from the standard arrangement onto n, and dropping K from the permutation IJL. If Q equal 1 and K equal 1 are both in the first position, they can both be dropped from CKQ to give MKQ. If Q is in the queued position, okay, so basically if we move AKQ to the top left, everything is much simpler. And every time we move AKQ closer by one step, we adding a -1 because of this rule over here. Whenever you change two rows or two columns, the determinant becomes negative instead. So after that, you get the determinant equals the sum of the product of element AKQ multiplied by MKQ, the minor, and multiplied by -1 to the power K plus Q. Going back, it is easy to see that the minor is the determinant of the reduced matrix constructed from A by removing the kth and qth column. We call it the minor of the element, and the expansion here, the Laplace development of the qth column, with Q between 1 and n. Equation 2.2 is the Laplace development of the first column. Since rows and columns, the matrix can be interchanged without changing the value of the determinant. We can obtain the Laplace of the kth row as well without. You can take the Laplace of the row or the column. The Laplace development of the second row for 3 by 3 is this. All 6 Laplace developments of a third order determinant. All 6 Laplace developments of a third order determinant by column, 3 by column, 3 by row, are contained in. They are just different regroupings of the same 6 terms. Matrix inversion, an important application of the theory of determinants concerned with the inverse of a matrix, square matrix. For a 2 by 2 matrix, the inverse is A1, A2. Okay, you need to change this to get A22, A11 minus A12 minus A21. So let me get another color. We switch around these two guys. And then you make these you make these guys negative, and that's it. Switch these guys around. Switch these guys around. Make these negative. This result can be verified directly by showing that the inversion relations AIA, AAI satisfied. 2.35 shows that it doesn't exist if determinant is not equal to 0. It exists only if determinant is not equal to 0. The inverse matrix can be constructed by using a more general form of the Laplace development. Okay, the inverse. So you can get this from the Laplace. How? How? The inverse matrix can be constructed readily by using a slightly more general form of the Laplace. Okay. So Since we normally the Laplaces give a determinant, right? So that's just a number. But we're trying to get a matrix, which is a bunch of numbers from the Laplace. So every calculation we do, we actually ending up with an element instead of like a number. Well, the element is a number, but still. Okay. More general form. Delta ik, carga delta ik, determinant of A equal from Q equal 1 to N A I Q C K Q equal A C transpose I K equals C A transpose K I. The inverse matrix can be constructed from the Laplace development of the ith row. Well, the Laplace development of the ith column gives, okay, the ith row gives you this stuff, the ith column gives you this stuff. What's the difference? I might need to like erase some stuff because it's getting too wild. Getting too wild. Okay. So it's ith row, ith column. What's the difference? IKKI. So we just switch around the indices to be like, oh, that makes sense. Maybe ACT CTA KI ACT CTA. Well, we also switch around the indices. Switch around the indices was not enough, apparently. Doesn't this and this have zero difference? Because Cronk delta IK is the same as Cronk delta KI, right? But there's no difference in this. The Laplace of the ith row is this. Ith column is this. You expect the Laplace to be equal anyways because you don't expect there to be two different inverses. So I agree with this, that these two should be the same. What about here? Ith row. Laplace of the ith row. What does that mean? That means let's just do the first row. That means we're using this guy. We're using one row, and we're doing like cofactor shenanigans with that row. Cofactor shenanigans with that row. IK. The inverse matrix can be constructed vertically by using a side image of Ki. Ki equals CAT Ki ACT AC CA. I need to do I have space anywhere? I can do it, yeah. Alright, let's just make some really simple examples. Let's do 1, 2, 3, 4, A, B, C, D. Okay. ACT, right? We call this A. We call this C. A transposed is A transpose would be 1, 4, 2, 3. C transpose would be A, D, B, C. Yeah, yeah. Okay. Now let we do CTA. CT multiplied by A. The first the C T A. The first element would be A 1A plus 3C. A plus 3C. This guy would be 2A plus 4C. 2A plus 4C. This guy would be B plus 3D. This guy would be 2B plus 4D. Now do for we do for CTA. Now for CAT. Okay, I initially planned to do only 2, but I guess I'll do 3 because I think we could get useful information from 3. Okay, well, what are we finding now? CAT. CAT. CAT is AB. CAT. AB. A plus 2B. A plus 2B. CAT. Next up we have this times this. 3A plus 4B. Next up we have this times this. C plus 2D. Yeah, C plus 2D. Then we have 3C plus 4D. Now let's do CTA. CTA equal CTA this times this. This times this. A plus 3C over here would be. Wait, have I gone mad? Have I gone mad? We already did CTA. We need to find ACT. 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 This times this. This times this is A plus 2B. This times this. This times this. This times this. C plus 2D. Now we have 3A. This times this. 3A plus 4B. This times this. 3C plus 4D. I feel like I did this wrong. It's just a feeling I have. CAT, right? CAT. This times this. AB, A plus 2B. This is this times this. 3A plus 4B. This. This is this times this. C plus 2D. This times this. 3C plus 4D. CTA, CTA. This times this. A plus 3C. This times this. 2A plus 4C. This times this. B plus 3D. This times this. 2B plus 4D. Okay. Alright. Um, yeah, let's see what we can do, what we can do with this now. Okay, the ik element of ACT should be the ki element of CAT. ACT CAT. ACT CAT. A plus 2b is 3 plus 4d. C plus 2d 3a plus 4b. Okay. CA, well, let me write this here. CA transpose equal to A C T A plus 2b 3 plus 4d. Yeah, so this guy transposed is equal to this guy, and the opposite too. The CAT transpose is over CTA. 3A. These guys are not really similar at all. Okay, so the transpose of the product of this is just transpose of this is this. CAT, CT. CAT. Is that a rule in general? ACT transposed. Okay. Um. Um. So without any shenanigans, these two guys is equal no matter what. Like even outside all this inverse stuff, these guys are equal. We're saying this is equal to this now. We're saying if I equal k, if I equal k, then determinant of A equals if I equal k, determinant of A equals the II element. Is that true? Determinant of A is equal the element, like any of the diagonal elements of CAT. That doesn't sound true. KI ACT. Maybe it is true, but you're saying A plus 2B is equal to 3C plus 4D? That's what you're saying? Like, if I is equal to K, right? This guy is 1. So determinant of A is just by itself there. And this guy just means element, a single element, Ki. The, if I equal to K, then this is II, right? So 1, 1, 2, 2, 3, 3, 4, 4. So that's just the diagonals in a matrix, the diagonal elements. So the diagonal elements of CAT, this is equal to the determinant. So the determinant is A plus 2B, 3C plus 4D. Determinant of A. Wait, how does this... Wait. Okay, okay, okay. C is the cofactor matrix, right? Yeah, so it's not as simple as A, B, C, D. Okay, okay, yeah, I can see it making sense then. Since C is special, it makes more sense. CAT. Cofactor. Cofactor. Cofactor matrix. Okay, let me Google something. Does a cofactor is the cofactor matrix the same order as the original matrix? Hopefully that's good enough of a question. Yes, the cofactor matrix always has the same order as the original. If your original matrix is n times n, then the cofactor matrix is also n times n. Each entry in the cofactor matrix is wait. I meant cofactor, not cofactor matrix. Is the cofactor the same as the original? A cofactor itself is not the same order as the original matrix. A cofactor is a scalar value. Cofactor is a scalar value. Hmm. Okay. 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 The cofactor is a number. Cofactor? Oh yeah, for real. This KQ means this is the location of the cofactor. Okay. I should Google stuff more often. Okay. I kind of want to reread all this now. Oh my god. I'll just skim it, okay? The expression we determined is the sum determines. It's called Laplace. To obtain Laplace, we factor out any one matrix element. Say that bling, where the cofactor is this. It does not contain AQ. The sum does not involve K. These restrictions are denoted by the primes. A reduced determinant of order n minus 1. Okay. Okay. Determinant of A. Hmm. Okay, well, let's just continue. Maybe afterwards I'll ask a bunch of questions to Google. Okay. Where were we? While the Laplace of the I column gives this. We wrote these results. The identity equal this. The A inverse equal the cofactor matrix cofactor matrix transposed divided by determinant of A, where C is the combined cofactor matrix whose matrix elements the cofactor CK share. Since the cofactors always exist, it follows that inverse matrix all exists if determinant is not equal to 0. If the inverse exists, is called invertible or non-singular. Invert the matrix this. First calculate determinant of A to see if it's invertible. Do the Laplace, you get the Laplace, you get this. The cofactor matrix constructed from the sign minus. Yeah, okay. Okay. Simultaneous equations. Determinants are also involved in the solution of simultaneous algebraic equations. Determinants are also involved in the solution of simultaneous algebraic equations. If we have n algebraic objects, that is n unknowns. If we have n unknowns, if we have n equations with n unknowns, so yeah, it's solvable, yes. These equations can be written down very compactly in matrix form AX equals C, where A is the n by n matrix, X equal this, and C equal this. N, where A is n by n matrix, and X and C are ND column vectors. D or ND. 3D column vectors, 4D, 5D. Left multiplication with A minus with the inverse then gives the unique solution. So if we multiply A minus 1 both sides here, on the left, so left multiplication, that implies left multiplication, and right multiplication is a thing we can do. So A minus 1 goes on your left, A minus 1 goes on your left. That leaves us with X equal A inverse C. So x1, x2, dot dot dot, xn equal the inverse matrix and the solution C1, C2, dot dot dot, Cn. If the inverse exists, you get a solution if the inverse exists. This requires that, yeah, equation, this reworded as xi equal. So if you want to find out x3, you have to x3 oh wait, okay, let's say this has to be square, right? So 4 by 4, and we say we have 4 guys here, so there's a 4 by 1, there's a 4 by 1 matrix. So the resultant matrix after this gets multiplied is a 4 by 1 matrix. Okay, so the result will be a 4 by 1, which, okay, it makes sense because the left side is also a 4 by 1. Alright, so xi equal di, yeah, the third x is the third element of this, equal the summation of j. Oh my god. Okay, summation of j, ctj. Okay, we're just shoving back our equation of an inverse over here. An inverse matrix is shoo. Inverse matrix is what is the cofactor thing? Inverse of A equals the cofactor transpose over the determinant of A. So we just shove that in over here. Um, the I element, summation J. Hmm. I'm trying to figure out the notation. The summation J. Okay, okay. C A inverse is CT determined A. Let me try and write this myself. CT determine A. Multiply by column guy. Um, the ith element of all of this. Yeah. Okay. Hmm. The ith element of all of this. CJ. I'm trying to figure out how this I here became IJJ here. Like, I don't really, I guess I don't understand too much of Einstein notation. It's called Einstein notation. Did he actually make it though? Um, summation J. The numerator of this expression looks like a Laplace of the ith column of determinant. Laplace of the ith column of determinant. This is indeed the case. The determinant is that of a modif. The determinant is that of A modified by replacing its ith column by C. This is called Kramer's rule. Laplace development of the ith column. The Laplace development does normally look like this. Summation of epsilons. You have the epsilon. You have the guys. CT looks like a Laplace development I column. This is indeed the case. CJI. Chronica Delta. Chronica Delta JI. Solve the matrix. We'll come back to this. Okay, let me just reread it real quick. These equations can be, you can get like this, you can get like this. Is you jump from here to here is xi equal this, yeah, yeah. From here to here, you know, this is just the indices. It's just the indices. Okay, we try to find out for one singular guy. How do we get one singular guy? A inverse, A inverse. How do you get one singular guy? Okay, okay. I think I'm getting closer. So let's just fill in these things. 1, 2, 3, 4, 1, 2, 3, 4. 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. To find out this guy, we had to multiply this column with this row by this column. So this times this times this times this times this. So to find out, yeah, I understand. Okay, CJ. Okay, so we're trying to find out X3, right? So we're interested in the third. Hmm, hmm. We're trying to figure out X3. So we're interested in this third result here. And to get that third result, we need to sum up the product of these elements with C. Okay. These elements is row 3 and all the columns. Sum up all the columns. So CT row 3, all the columns, and we summon up all the columns of C as well. So yeah, I agree. What about here to here? Determiner, going C transpose. Oh yeah. C transpose IJ is just CJI. That's just normal. Okay, good. The numerator of this expression looks like Laplace of the ith. Yeah. The determinant of the ith column. The Laplace form of the ith column. Laplace form of the ith column. Laplace development like this multiplied by cofactor. This is indeed the case. The determinant is that of A modified by replacing its ith column by C. Of the ith column of a determinant. Of the ith column of a determinant. Ooh. Oh. Oh, yeah. I understand. I was confused because we're dealing with rows here, but when we transpose it, we're dealing with columns now. So it's actually third column. The numerator of this looks like the Laplace of the third column of the ith column of a determinant. This is indeed the case. The determinant is that of a determinant is that of A modified by replacing its ith column by C. Bling, bling. We will work with this. Solve the matrix equation this. Since determinant of A is 2, I guess we're calling this A. We have a Kramer's rule. Okay. This is called Kramer's rule. We have by Kramer's rule x1 equal okay, Kramer's rule. Well, let's rewrite this to look like this. Xi equal 1 over the determinant of A, and apparently this is a determinant. That is a determinant of CJI. CJI. Wait. Something happened there. when they transposed this, they also had to switch around the order. How come? How come? How come? Rover column. I. Oh, hmm. CJ, CJI. CJ. CJ. CJI. J. Row. I column. Hmm. 1 2 1 1 1 3 1 2 3. Okay. 1 2 1 1 1 3, and we just put our C vector into here. Hmm. Apparently that is CJ CJI. CJ CJI. Determinant. Cofactor. What is cofactor? Cofactor is what is cofactor? Cofactor is the limit stuff. Cofactor is the limit stuff. CJ CJI is a matrix of cofactors. I'll look into it later. So to find x1, you just put the C column into the first row. X2, put the C column row 2. For x3, C column row 3. Compute it. That these are the solutions can easily be verified. What is the question? Solve the matrix equation this. That these are the solutions. That these are the solutions can easily be verified by doing metric multiplication into AX. Into AX. What did I mean by that? We start off with AX. Yeah. So if we just multiply our A by our seemingly answer, we should get 1 2 3. Some questions here. I don't feel good about today for some reason. Homogeneous equations. It is also possible to solve a set of n homogeneous equation, algebraic equation, written in the form ax equals 0. That is, if c is equal to 0. It is obvious that there is a unique solution x equal inverse of c equals 0. It's obvious that there is a unique solution x equal inverse c equals 0 if a is non-singular. So that is if a could be inverted. We call this trivial case. A non-trivial solution is one with x not equal to 0. So one of the answers is x equal to 0. All the x's is 0. This can only occur if the term a non-trivial solution is one with x not equal to 0. This can only occur if determinant of a equals 0. Non-trivial solution. Are we going into complex plane or something? In non-trivial solutions, one with x, yeah, yeah. This only occurs if determinant of A is not equal to 0. What do we do then? For then, we have the quotient of two zeros, which can be finite. The quotient of two zeros can be finite. 0 and 0. I guess. Sure. It's weird. To see what we are getting into, let us consider the simple case 2 by 2. Then ax equals 0 means the two simultaneous. Ax equals 0 means this. Okay. A11, A22, A11, A12, A22, A21, X1 and X2. This times this. A1, yeah, good. These equations state that x equal x1, x2 is perpendicular to the row vectors. These equations say that x is perpendicular to the row vectors A11, A12, A11, A12, and A21, A22 contained in A. These equations say that hmm, hmm, hmm. That is x is a vector, any vector, perpendicular, x is any vector perpendicular simultaneously to both A1 and A2. So x is a vector. It needs to be perpendicular to A1 and A2. Its length is of no consequence in the homogeneous equation. Only its direction can be determined. If the two row vectors are non-parallel, determine A does not vanish. If two vectors are non-parallel, we determine A could still exist. Non-parallel means that if the x vector is in the x-axis, the two row vectors in A1, the two row vectors of the A matrix cannot be both in the y-axis. Yeah. So one has to be in the y, one has to be in the z, like how I first drew it here. Yes. No. If okay. There is then no non-trivial solution. If the two row vectors are non-parallel, I mean one in y, one in z, determinant does not vanish. There is then no non-trivial solution. There is no non-trivial solution. No, there is yes. There is yes a trivial solution. Okay, so there's only the trivial solution if one is in the y, one is in the z. An x perpendicular to this plane cannot also lie in it. So the y and the z of determinant of matrix A makes up a plane. X cannot lie in that plane. No, an X perpendicular to this plane cannot also lie in it. Yeah, obviously. There is thus no solution X in the plane. This is the reason why determinant A equals 0 is required. So A equals 0. Determinant A equals 0 can be obtained by making A1 and A2 parallel. I feel like they're saying the same thing over and over. Determinant A equals 0 can be obtained by making A1 and A2 parallel. Let me drink some water and then I'll reread this. It's also possible to solve a set of n homogeneous algebraic equation. Okay, let me bust Google out. What is a homogeneous algebraic equation? Homogeneous algebraic equation is one where every term contains the same total degree of the variables. Examples: 3x plus 2y minus c. Each term has x cubed. So in physics, this would mean that all the terms have the same unit. Okay. Alright, a homogeneous equation is one where one homogeneous equation is where everything have the same degree. So x squared plus xy plus y squared, all of them have the same degree. This is made out of two x's, this is made out of two stuff. If you add 6, it's no longer homogeneous because this guy is made out of 0 x's. This would also interrupt the homogeneousness because this is made out of 1x. I asked if it was similar to physics because m squared is meter squared area. M times m squared is still area. This is still area. This is nothing to do with area. So you can't add these together. These is the area, these is not the area. This homogeneous, these interrupt the homogeneous. Okay. Solve a set of n homogeneous equations written in matrix form. Okay. C is equal to 0. It is obvious that there is a unique solution. It's obvious that there is a unique solution where x is equal to 0. If I need to write this down because it's a little confusing. A non-singular, A non-singular, no inverse. Yeah, that what that means? No inverse. No A minus 1. x equal 0 is solution. We call this trivial case. Trivial. Trivial. A non-trivial solution is one where x is not equal to 0. Okay. X not equal to 0. Non-trivial case. Non-trivial. Only occur if determinant A equals 0. Wait. We call this a trivial case. A non-trivial solution is one where x is not equal to 0. This can only occur if determinant A is equal to 0. What do you mean this? Do you mean this as in trivial? Or this as in non-trivial? I assume they mean this as in trivial, because if A equals 0, then the inverse doesn't exist. So I assume that's for the 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 trivial one. Determinant A equals 0. And I think this is a necessity. Necessity. Because this can only occur if A equals 0. Determinant A equals 0. Then we have, wait. Now they're saying for then we have a quotient of two zeros, which can be finite. So that makes me think, oh, maybe it's non-trivial. But then we have the quotient of two zeros, which can be finite. Good. Let's just continue. To see what we are getting to, let's first consider the simple case. Do I do ax equals 0 means the two simultaneous? Yeah. These equations state that blah this perpendicular to these row vectors. Row vectors. This. Row 1, row 2. Yeah. That is, x is a vector. Any vector. Wait. This is dot product here, right? This times this is dot product. This is secretly row 1 dot producted with x. Row 1 dot producted with x. This is secretly row 2 dot producted with x. And if that is equal to 0, that means it's perpendicular, right? Dot product is rx cos theta. Rx cos theta. If this is equal to 0, then I mean theta is equal to, it either means the row r, it either means r is equal to 0, x is equal to 0, or theta is equal to 90, which means perpendicular. So let me write that. Theta equal 90, or x equal 0, or r equal 0. Yeah, r2. What logic symbol can I put here? R2. Okay, I'll just put Ri, because then I would have to be like theta 1, theta 2. theta I. Okay. Um, sh show that this perpendicular to this. That is, x is a vector, any vector perpendicular simultaneously to both a1 and a2. Its length is of no consequence in a homogeneous equation. Homogeneous. The length of x does not matter to the vectors on matter because theta is 90. Um, only its direction ex or e minus x can be determined. If the two row vectors are non-parallel, determine A does not vanish. Non-parallel, determine A does not vanish. Oh, girl, let me Google this now. There's non-parallel um, does non-parallel also discount anti-parallel? Non-parallel excludes both parallel and anti-parallel. Okay, so not parallel at all in any context that it would. Okay, if two vectors are non-parallel, determine A does not vanish. So what does that mean? That means that there is hope for a non-trivial solution. Determinant of A e hmm, hmm, hmm. If R1, R2, and X like perpendicular or something, I don't know. Then determinant of A is alive. Is alive. Oh my god. Alive. Okay. Um there is then no non-trivial solution. There's then no wait, what? If the two I what? Okay. There's then no non-trivial solution. The reason is that a non-trivial solution is one with x have something in him. That is a non-trivial solution. X have something in him. Yes, x have something in him. If this thing is true, there is then no non-trivial solution. No non-trivial solution. There's no way we have a non-trivial solution. There's no way x have something in him. X is 0. Is that what we're saying? Uh, if the two row vectors are non-parallel, determine A does not vanish, and x is nothing. X is nothing. Determinant of A does not vanish. Hmm. Hmm. Non-trivial. I feel like I'm just reading contradictions. Or is it in my head? Okay, I'll just read. I'll just read. Okay. Um, there's an if the two vectors are non-parallel, determinant A does not vanish. There is a no non-trivial solution, so X has nothing in him. The region of A1 and A2 already span the entire 2D plane of the problem. An X perpendicular to that plane cannot also lie in it. There is thus no solution X in the plane. There's a reason why determinant A equals 0 is required. There's no none. Determinant A equals 0 can be obtained by making A1 and A2 parallel. I skimmed this like a while ago and I understood it. Oh my god. Hmm. Hmm. Let's let us try again. Um, it's obvious that there is a unique solution. X equals 0 if A is invertible. Yes. We call this a trivial case. Trivial, X equal to 0. A non-trivial solution is one with X have something. This could only occur if determinant A is equal to 0. X have something could only occur if determinant of A is equal to 0. Determinant A equals 0. Okay. Wait. X equal A inverse determinant A. But then we have the quotient 2 zeros, which can be finite. To see what we are getting into, let us first consider the simple case of divided by 3%. Ax equals 0 means 2 some yeah. These equations state that x are perpendicular. X is in fact perpendicular to euro vectors. That's a fact. A fact. That cannot change. That is, x is a vector, any vector, perpendicular simultaneously to both of them. The length, we don't care about the length. Only the direction we could ever find out. If the two row vectors are non-parallel, two non-parallel, 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 the two non-parallel, if the two is non-parallel, the determinant A does not vanish. If there was parallel, would they vanish? If there was parallel. If it was parallel, that meant that these two columns would be the same. These two rows would be the same. Yeah? Yes. So then it would be, the determinant would be 0. So that way it needs to be non-parallel. If they're non-parallel, the determinant exists because we have different numbers, so it's not the same. Okay, let me write that. Parallel um, arrow, I don't know. Parallel numbers the same, determinant equal 0. 2, 1, 2, 1. Okay. That's enough for future me to be like, oh yeah, I get it. Um, 8 is not vanished, yeah. There is then no non-trivial solution. No non-trivial solution. The trivial is A equals 0. The non-trivial, it has something in it. A have something, X have something in it. The determinant exists. Let me be like, why can the quotient of two zeros be finite? Maybe that is the source of my confusion. The usual rule in standard arithmetic and calculus is undefined because 0 divided by anything non-zero is 0. Anything non-zero divided by 0 is undefined or infinite. 0 divided by 0 could be anything, depending on context. So why do we sometimes get a finite value? In limits, especially in calculus, we encounter stuff like limit as x approaches a, f on g equals 0, 0. This is called an indeterminate form. It doesn't mean the limit doesn't exist. It means we need to analyze further. Example, as x tends to 0 of sine x on x. Even though both numerator and denominator go to 0, the ratio approaches a finite value 1. Sine x, x, x. As x approaches 0, sine x approaches 0, approaches a finite value 1. Quotient of two zeros can be finite when we're dealing with limits. The rates of vanishing of numerator and denominator are balanced. Okay, I guess. Alright. So 0 divided by something is 0. Something divided by 0 is insane. 0 divided by 0 could be a thing. Um, it has to do with limits, okay? Okay. If two vectors not parallel, determinant A does not vanish. There is a no non-trivial solution. A trivial solution is where x is 0. Non-trivial solution, x has something in them. There is no way x have something in them. Why? No way x have something in them. If x had something in them, a times x. Okay, I understand. I understand. If x had something in them, then AX would give something, it wouldn't give 0. So X needs to be 0 if A exists, right? I, we'll go with that logic. We'll go with that logic. Um, the reason is that A1 and A2 already span the whole of the 2D plane of the problem. An X perpendicular to this plane cannot also lie in it. An X perpendicular to this plane cannot also lie in it. There's just no solution X in the plane. There's a reason why determine AX equals 0. An X perpendicular to this plane can also lie in it. No solution X in the plane. Correct. I agree. This is why determine A equals 0 is required. Determine A equals 0 can be obtained by making A1 and A2 parallel. They then occupy only one of the two dimensions of the problem, leaving the other dimension for X. The direction of X is then uniquely determined up to a sign. For true matrices, AX equals 0 means that X must be perpendicular to all three rows vectors of A. AI dot X equals 0. Suppose two of these vectors are not parallel. Suppose two of these row vectors are not parallel to each other. To obtain determine A equals 0, the row vector must be made up of a linear combination of these non-parallel vectors. To obtain determine A equals 0, the third guy must be made up of the first two guys. This means that this A3 lies in the plane A1, A2. The three row vectors only span 2D plane. This shows that X is a normal to this plane through the origin. X is a normal to this plane through the origin. All vectors are measured from the origin. Again, only its direction is determined, not its tensor length. Determinant of A equals 0 is also realized when all three row vectors are parallel to one another. Hmm. I'm understanding, right? I'm understanding a bit, but I think it'll just be better if I do this like another day, like tomorrow. So the end of stream. Um, Goodbye.